the Sun is the only star whose interior we can genuinely probe, and for that reason it is less a light in the sky than a physics laboratory of unrepeatable value. Every other star in the universe is a point of light, interpreted at last by analogy to this one. The Sun alone is close enough, some 250,000 times nearer than the next nearest star, that we can weigh its layers, listen to its ringing, and catch the very particles born in its core. This chapter treats the Sun accordingly, not as a source of warmth but as a structured, self-regulating engine whose every major part is now anchored to direct measurement. We shall descend through its nested shells, the fusing core, the vast radiative zone, the boiling, convective envelope, and then meet the three great windows through which modern physics has confirmed the whole picture from the outside: the trembling of its surface, the neutrinos that pour from its heart, and the magnetic cycle that beats through it every 22 years. Quantitative work begins with a handful of global numbers, which modern astronomy fixes not as measurements but as exact defining constants, agreed by international convention. The Sun is a yellow main sequence star, and its power output, its radius, and its surface temperature are all declared standards, so that a star described as 2 solar luminosities means exactly twice that agreed figure. The surface temperature repays a careful definition, for it is widely misunderstood. The quoted value of about 5,700 Kelvin is the effective temperature, the temperature of an ideal blackbody that would radiate the Sun's total power from a sphere of the Sun's size. It is therefore a single number standing in for a whole range. The visible surface spans many temperatures, and the center is some 2,500 times hotter still. To speak of the Sun's temperature as one figure is a convenience of bookkeeping, not a description of any single layer. The framework that connects these surface numbers to the hidden interior is the standard solar model, and it rests on 4 classical equations of stellar structure. The first simply accounts for mass layer by layer. The second is hydrostatic equilibrium, the balance, at every depth, between the inward crush of gravity and the outward push of pressure. The third conserves energy, tallying the power generated by fusion. And the fourth governs how that energy is carried outward, whether by radiation or by convection. Closed with the physics of the gas, its opacity and its nuclear reactions, these equations are integrated from the center to the surface. The model is then calibrated. A small number of free parameters are tuned so that a ball of 1 solar mass, aged 4.5 billion years, reproduces the Sun's observed brightness and radius exactly. Its real power lies in everything it is not tuned to match: the interior sound speed, the depth of convection, the neutrino output, each of which becomes an independent test. The backbone of that structure is hydrostatic equilibrium. The Sun neither collapses nor explodes because, at every depth, gravity's inward pull is exactly balanced by the outward gradient of pressure. Integrating that balance from the center outward yields the run of conditions through the interior, and the ranges are staggering. At the core, the temperature reaches about 15 million Kelvin, the density some 150 times that of water, denser than lead, and the pressure hundreds of billions of times that of the air at sea level. From there, all three plunge steeply outward, until at the visible surface the gas is cooler than a candle flame and thinner than the Earth's atmosphere. The surface we see is thus a tenuous skin upon a star far hotter and denser within than any intuition allows. And, built into this balance is a strange thermostat. A self-gravitating gas has, in effect, a negative heat capacity, lose energy, and it contracts and heats, so that any flicker in the core's output is automatically damped, holding the Sun steady for billions of years. Fusion is confined to the innermost quarter of the Sun's radius, a region holding a third of its mass, yet generating essentially all its light, and that it happens at all is a triumph of quantum mechanics. 2 protons approaching each other are pushed apart by their like electric charges, and at 15 million Kelvin the typical colliding pair carries barely 1,000th of the energy needed to smash through that barrier by brute force. Classical physics, then, forbids the Sun to shine. Quantum mechanics permits it through tunneling. There is a small but non-zero chance that a proton simply passes through the barrier it cannot climb, a probability that plunges steeply as the energy falls. The Sun burns only because in the crush of its core, a vast number of protons make a vast number of attempts, and a rare few tunnel through. The stars are lit by one of the subtlest effects in all of physics, the leakage of particles through walls they classically could never cross. The rate of fusion is set by a delicate contest between 2 opposing trends. On the one hand, the hotter, faster particles that tunnel most easily are exponentially rare in the thermal crowd. On the other, the tunneling itself grows exponentially more, likely with energy. The product of these two opposing curves is sharply peaked at an energy far above the average yet far below the barrier, the gamma peak, and it is within this narrow window of energies that essentially all solar fusion occurs. Because the whole process depends so steeply on temperature, the reaction rate climbing roughly as the fourth power of it near solar conditions, the burning is exquisitely sensitive to any change in the core's heat, and it is this sensitivity that furnishes the thermostat. Warm the core a little and it burns furiously, expanding and cooling itself back. Cool it and the fires bank down. The stability of the sun over eons is written into the mathematics of that peak. The dominant pathway is the proton-proton chain, which supplies over 98% of the sun's light, with a catalytic carbon-nitrogen-oxygen cycle making up the rest. Its net effect is to fuse 4 hydrogen nuclei into one nucleus of helium, releasing about 26.7 million electron volts of energy, a little of it carried invisibly away by neutrinos. The crucial fact is the slowness of the very first step, in which two protons must not only tunnel together, but in the same fleeting instant, one must transform into a neutron by the feeble weak interaction. So improbable is this coincidence that the average proton in the core waits billions of years to undergo it. That bottleneck is a blessing. It is precisely why the sun sips its hydrogen so slowly that it can shine for some 10 billion years, rather than detonating in an instant. The leisurely pace of the sun's life, and thus the time available for life on Earth, hangs on the reluctance of that single reaction. Above the core, out to about 7/10 of the radius, lies the radiative zone, where energy travels not by the motion of the gas but by radiation seeping through it, and its journey is astonishingly slow. A photon born in the core travels only a tiny fraction of a centimeter before it is absorbed and re-emitted in some random new direction, and then again and again in a staggering random walk. Because a random walk drifts outward only as the square root of the number of steps, escaping the sun this way requires a number of steps almost beyond comprehension, and the energy released by fusion takes on the order of 100,000 years to work its way to the surface. The sunlight that warms your face today was liberated in the core when the last ice age was only beginning. This immense delay also buffers the sun. Any change in the nuclear furnace is smeared out over tens of thousands of years before it could ever reach the surface, making the star a supremely steady beacon. At about 7/10 of the way out, the character of the sun changes abruptly. The cooling gas grows more opaque, radiation can no longer carry the flux and the plasma begins to boil. Great columns of hot gas rise, spill their heat near the surface, cool and sink, carrying the energy the final third of the way by convection. This churning writes itself onto the visible face of the sun as granulation, a restless, ever-shifting mosaic of bright cells about 1,000 kilometers across, each a column of rising gas, ringed by darker lanes where the cooled gas plunges back down. Each granule lasts only minutes. A larger pattern of supergranulation, tens of thousands of kilometers across, persists for about a day. These are not mere surface decoration. The hammering of the convective gas against the layers above rings the sun like a bell, exciting the oscillations that will let us see inside it, and the same restless motions drive the dynamo that builds its magnetic field. Modelling this convection from first principles is notoriously hard, for it is fully turbulent and spans a vast range of scales, and the standard solar model finesses it with a simple approximation called mixing length theory. A rising blob of gas is imagined to travel a certain characteristic distance before dissolving and giving up its heat, and that distance is one of the free parameters tuned to make the model fit. It is an acknowledged crudeness. The theory captures the bulk effect of convection, but not its true dynamics, and it is increasingly being replaced by three-dimensional simulations that follow the boiling gas directly. The visible surface itself, the photosphere, is simply the thin layer, only a few hundred kilometers deep, from which light can finally escape into space, which is why the sun, though wholly gaseous, has so sharp an edge. Above it lie the tenuous chromosphere and the searingly hot corona, but those belong to the physics of the sun's atmosphere, not its interior. Photons, then, arrive tens of thousands of years old and utterly reprocessed, but there is a messenger that leaves the core untouched. Neutrinos, produced in every fusion reaction, interact so weakly that they stream straight out of the sun in about 2 seconds and reach the Earth in 8 minutes, carrying a real-time report from the very center. They are the only direct probe of the nuclear furnace, and the standard solar model predicts their flux precisely. Yet when Raymond Davis first captured them in the late 1960s in a great tank of cleaning fluid deep in a South Dakota mine, he found only about a third of the predicted number. This shortfall, the solar neutrino problem, persisted for 3 decades, confirmed by experiment after experiment, and posed a stark choice. Either the model was wrong about the sun's core, or something befell the neutrinos on their way to the Earth. The resolution, when it came, favoured the neutrinos, and it rewrote particle physics. The Sudbury Neutrino Observatory, a great sphere of heavy water 2 kilometres underground in Canada, could do what earlier detectors could not: distinguish the electron-type neutrinos the Sun emits from the other 2 types, and also count all 3 together. It found that while the electron neutrinos were indeed only a third of the prediction, the total across all 3 types matched the standard solar model exactly. The missing neutrinos had not vanished, they had changed flavour, morphing from one type into another during their flight from the Sun, a metamorphosis to which the earlier experiments had been partly blind. This single result both vindicated the model of the Sun's core and proved that neutrinos have mass and can oscillate, physics beyond the reigning theory of particles, and worthy of 2 Nobel Prizes. The conversion is even enhanced within the Sun itself, by the neutrino's passage through its dense matter. The final confirmations came from an exquisitely pure detector beneath the Gran Sasso mountain in Italy. Where earlier instruments could catch only the rare, high-energy neutrinos, Borexino was clean enough to detect the low-energy ones, and in 2014 it directly measured the neutrinos from the very first dominant step of the proton-proton chain, watching in real time the reaction that powers the Sun. Then, in 2020, it accomplished something subtler still: the first detection of neutrinos from the catalytic carbon-nitrogen-oxygen cycle, at a rate of only a few counts a day, proving that this secondary burning mode, the one that dominates in stars heavier than the Sun, truly operates in our own star's core. Between Davis's first tank and Borexino's last count, core fusion was transformed from a theoretical inference into a measured fact, reaction by reaction, and the Sun became a calibrated source for the physics of the neutrino itself. The second great window into the interior is Helioseismology, the study of the Sun's natural vibrations. The ceaseless buffeting of the convection sets the whole star ringing, exciting millions of sound waves that resonate through its body and show up at the surface as tiny rhythmic heavings, with a dominant period near 5 minutes. These are pressure waves, and because sound travels faster in the hotter, denser depths, a downward plunging wave is gradually bent back toward the surface, each mode trapped in a shell of the Sun whose depth depends on its wavelength. Shallow modes probe only the outer layers, the deepest reach to the very core. By measuring the precise frequencies of these millions of modes, physicists can invert the pattern to read the temperature, density, and motion along the path each wave travels, exactly as earthquakes reveal the interior of the Earth. The Sun, it turns out, is a bell whose overtones encode a map of its own inside. Reading that bell has taken a global effort. Networks of telescopes spaced around the world watch the Sun continuously, handing off from station to station so that the ringing is never interrupted by nightfall, while spacecraft observe it unblinking from space. Inverting the accumulated frequencies has yielded the run of sound speed and density through nearly the whole interior to better than a fraction of a percent, and the results are a triumphant confirmation of the broad standard picture. Helioseismology fixes the base of the convection zone at 713 thousandths of the radius, measures the abundance of helium at the surface, and maps the internal rotation, all quantities the model predicts rather than fits. There is one sharp exception, a stubborn 1% discrepancy in sound speed just beneath the convection zone to which we shall return. A more elusive prize, the gravity waves that would probe the core directly, remains contested and unconfirmed. But for the pressure waves, the Sun's interior is now the best measured stellar interior in existence. Helioseismology also revealed how the Sun turns, and in doing so exposed the engine of its magnetism. The surface does not rotate as a solid body. The equator circles in about 25 days, the poles in nearer 35, and this difference persists all the way down through the convective envelope. Beneath it, though, the deep radiative interior rotates almost rigidly, at a single rate. Between the two lies a thin zone of intense shear, the tachocline, where the rotation switches abruptly from differential to uniform, and this layer, seismology's great discovery, is widely believed to be the seat of the Sun's dynamo. There, the shear of the differential rotation stretches and wins the magnetic field, drawing a north-south field out into a powerful east-west one, coiling it ever tighter like a wound spring. The sun's magnetism is not a static relic, but a thing continuously generated out of the marriage of rotation and convection in its churning outer shell. The regenerating magnetic field drives the sun's whole restless activity, its sunspots, flares, and eruptions, in a great cyclic rhythm. Buoyant ropes of the wound-up field rise through the convection zone and burst through the surface as pairs of sunspots. The systematic tilt of these pairs, worked upon by the surface flows, slowly rebuilds the field in the opposite direction, and so the cycle turns. Every 11 years or so the sun's magnetic poles reverse, giving a full magnetic period of about 22 years. The most beautiful fingerprint of the process is the butterfly diagram. Plot the latitudes of sunspots over time, and they trace wing-shaped patterns, the spots first erupting at mid-latitudes and marching toward the equator as each cycle matures. Much remains genuinely unsettled. The exact seat of the dynamo is again under debate, and the deep cause of the great lulls in activity, such as the dearth of sunspots in the late 17th century, is still unknown. The solar cycle is observed in exquisite detail, yet not fully understood. For about 2 decades the Standard Model and Helioseismology agreed beautifully, and then in the 2000s that agreement broke, opening a tension that remains unresolved to this day. The trouble came from an improvement in measurement. The abundance of each element in the sun is read from the strengths of its dark absorption lines in the solar spectrum, and when astronomers replaced their old flat model atmospheres with sophisticated 3-dimensional simulations of the boiling surface, the inferred amounts of the abundant elements carbon, nitrogen, and oxygen fell noticeably. The sun's overall content of heavy elements dropped by 20 to 30%. On its face this was a refinement, resting on better physics, but it wrecked the concord with the interior, because the abundance of heavy elements controls the opacity, and the opacity controls the structure. Lower the heavy element content, and the opacity of the radiative zone falls with it, shifting the predicted depth of the convection zone and the interior sound speed away from what Helioseismology plainly measures. A model built with the new lower abundances predicts a convection zone too shallow, a surface helium too sparse, and a sound speed that disagrees with the seismic data by several standard deviations, where the older, higher abundances had fit within the errors. So the field faces a genuine conflict between 2 independent and well-founded lines of evidence. The finest spectroscopy points to the lower metal content, while the finest seismology insists on the higher. No resolution commands agreement. Perhaps the calculated opacities are wrong, and laboratory experiments have indeed found iron more opaque than theory predicted. Perhaps some abundance is mismeasured, perhaps some subtler physics is at work. Even the neutrinos have been enlisted, for the carbon-nitrogen-oxygen flux depends on the core's metal content. The solar abundance problem stands open, a reminder that even the best-known star retains a discrepancy the field cannot yet explain. Step back, and the sun emerges as a layered, self-regulating system whose every major part is now tied to direct measurement rather than to theory alone. Gravity compresses the core until quantum tunneling lights the proton-proton chain. Hydrostatic balance and the fierce temperature sensitivity of fusion together hold the output steady. The energy crawls out through the radiative zone over 100,000 years, and convection carries it the last stretch to a surface glowing at some 5,700 Kelvin. What sets the modern understanding apart from the picture of a century ago is that this interior is no longer inferred but observed. The neutrinos confirm that the core burns, and at the predicted rate. The trembling of the surface maps the sound speed and rotation within to a fraction of a percent, and the magnetic cycle with its marching sunspots displays the dynamo at work. 3 wholly independent windows, and through each one the same star. It is worth being honest about where the knowledge ends. The core fusion, the layered transport, the oscillation of neutrinos, the broad seismic conformation of the model, these are secure. But real questions remain sharply open: the 1% abundance conflict between spectroscopy and seismology, the precise seat and workings of the dynamo, the reality of the deep gravity waves, the cause of the long lulls in solar activity. These are not cracks in the foundation but the growing edges of the subject, each posed so sharply only because the surrounding physics is so firmly known. And this is the sun's enduring gift to science. It is at once close enough to be measured in exquisite detail, and ordinary enough that what we learn from it applies everywhere. Every other star in the heavens, Every point of light in every cluster and every distant galaxy is red in the end, by analogy to the one star we can truly know. To understand the sun is to hold a key to the stars.